Hi everyone, today I'll be giving a quick video presentation on counterfactuals for design. Thanks so much for tuning in. I'm aiming for around 15 minutes and I'll add relevant links in the description to explore for a deeper dive if interested. Alright, let's get started. So what are counterfactuals? Consider the following. You are trying to design a bike to fulfill a demanding set of design requirements. You have a concept design, but it's currently underperforming in several attributes. How should you change the design? What if you reduce the wheel diameter, for example? How would that change the design properties? What if you switched handlebar types, or what if you shortened the top tube? What if you did all three? Each of these what-if scenarios is a counterfactual, and most design engineers are intimately familiar with the use of counterfactuals as a reasoning tool, even if they may not consciously acknowledge it. Now, as engineers, we've developed many methods to help understand these counterfactuals. Numerical simulations, machine learning predictions, even something as simple as an empirical equation can help us predict attributes of a design. And what I've described here is the classic variety of counterfactuals, which I'll refer to as forward counterfactuals. And while forward counterfactuals are useful, they're not answering the question we're really interested in. The forward counterfactual asks, what if I make some modifications to my design? How do my design's properties change as a result? But what I really want to answer is the inverse counterfactual. What if my design meets all of my requirements? What would need to change about my design for it to do so? Now, this inverse counterfactuals question is much more challenging to answer. Most of the predictors we can use for a forward counterfactual are not reversible. Instead, to answer the inverse counterfactual scenario, we must often iteratively search through forward counterfactual scenarios before finding a suitable inverse counterfactual. So in my presentation today, I'll be proposing a method called Multi-Objective Counterfactuals for Design, or MCD, to tackle this problem. Now, MCD executes challenging inverse counterfactual search problems given an existing design and its properties, as well as a set of desired properties and one or many property predictors. And MCD effectively searches for designs that achieve the specified design goals, effectively answering the inverse counterfactual scenarios. Now, inverse counterfactuals in design fulfill the role of a customized design recommendation system. Imagine a design tool that tells you exactly how to modify your particular design to meet your specific set of design goals. No more painstaking iteration, no more overwhelming doubt about the millions of possible designs to consider. This is really the vision we're pursuing in this work, and I hope I can convince you today that with the rise of advanced AI models, coupled with the growing numbers of engineering design data sets, we are closer to this vision than you may expect. So before diving into the details of the counterfactual search process, I'd like to first consider what makes a counterfactual strong. So if we consider the literature surrounding inverse counterfactuals in fields like machine learning explainability, for example, researchers generally agree on several key attributes which we desire in inverse counterfactuals. I'll very quickly step through these attributes one by one with a quick discussion. So naturally, the entire purpose of inverse counterfactuals is to consider designs that achieve some counterfactual property. If they do, we consider them valid, and unsurprisingly, invalid counterfactuals tend not to be very useful. Next is proximity. Counterfactual features should be similar to the original design features. This means that counterfactuals will require smaller modifications to realize and will be more likely to preserve attributes of the original design. Not only should counterfactuals change design features as little as possible, they should also change as few of the original design features as possible. And we refer to this as sparsity. So sparsity and proximity are basically saying that we want our counterfactual to be as similar to the original design as possible. But we also want counterfactuals to generally resemble existing designs. In other words, the counterfactuals should lie near the design space data manifold. This manifold proximity, as we call it, is a bit less intuitive, but it ensures that our predictors stay accurate as we search the design space and make sure our counterfactual is realistic. Counterfactuals should also be possible to achieve or actionable. Since certain modifications to a design may be impossible, we'd like generated counterfactuals to adhere to user-specified actionability constraints. And we also care about diversity, meaning that sets of generated counterfactuals should be varied and achieve target properties through different means. The more diverse the set of generated counterfactuals, the higher the likelihood that at least one satisfies the user's needs. And finally, we also desire model independence. And model independence is less of a property of the counterfactual itself and more of a property of the counterfactual generator. And it says that counterfactual search should not require a particular type of predictor. And notably, for maximal generalizability, a good counterfactual search algorithm should ideally not require predictors to be differentiable. So this counterfactual search problem can actually be framed as a multi-objective optimization problem. We have proximity, manifold proximity, and sparsity as objectives that we optimize, while validity and actionability are treated as constraints. To achieve model independence, we can use a gradient-free optimizer such as NSGA2, which we use to solve the problem. And once a strong set of counterfactual candidates is identified by the optimizer, a diverse set can be selected in a sort of final post-optimization sampling step. So specifically, we use a performance-weighted determinantal point process to identify a diverse, high-performing set of optimized designs. And additionally, users can specify importance weights during the final sampling step to prioritize certain objectives over others. We'll go over a quick example to build some intuition into how this sort of decoupled optimization and sampling process works. So let's consider the simple two-dimensional test problem, and we'll assume that these two dimensions are two defining features of a simple design. So the central X is the starting design configuration, which we refer to as the query, and the gray regions are the regions that satisfy some counterfactual attribute, say maybe a safety factor greater than 1. And MCD has no prior knowledge of the regions satisfying the attributes, but we give MCD access to a simple attribute check that it can query at will. So here are all the solutions that MCD identified over a short optimization run, and we can easily see that the optimizer has focused on more proximal solutions which lie in the small circle. Next, after optimization is finished, we perform sampling. So we sample a set of 10 counterfactuals from the numerous designs identified through optimization, and the determinantal point process sampler simultaneously tries to select high-performing counterfactuals but maintain reasonable diversity. So we observe that it selected at least 1 point from each distinct region of the solution space, but the sampler focused on the most proximal region, the circle, which has the best proximity scores. However, we can also bias the sampling to focus on certain objectives over others. So for example, when focused on proximity, 9 of the 10 counterfactuals are sampled from the nearest region. When we focus on diversity, 2 points are sampled from each of the regions. And when focusing on sparsity, the counterfactuals are exclusively selected such that only one of 2 design features change, which completely excludes the nearest region, as we would expect. Okay, I'm now going to present a design example using the framed bike frame dataset. We've got a frame design that consists of 37 parametric values, including dimensions, tube diameters, tube thickness values, as well as material. The design properties we care about are weight and safety factor under a typical loading scenario. And to predict these properties, we've got an ensemble of machine learning models which were trained on the frame dataset. We have several equations serving as constraint checks to basically verify whether a given design configuration is geometrically valid. And to make the problem more challenging, we lock the material as a feature constraint requiring a steel bike. And finally, we specify a set of desired properties, of course, that call for a 20% increase in safety factor and a simultaneous 30% decrease in weight. And keep in mind, this is a fairly challenging ask since optimizing weight and safety factor typically don't go hand in hand. Now, MCD comes up with many designs that satisfy the requirements, 3 of which are shown here. And in general, it identified that the down tube thickness is a key structural shortcoming of the original design and has made significant changes to this parameter across all counterfactuals it generates. And though it's not shown here, it also optimizes the other 35 design variables to cut down unnecessary material and save weight, realizing the weight savings that we desired. So one other thing that I'd like to highlight is that the predictive models MCD uses can be very sophisticated if desired. So previously we gave an example with a simple regressor or a simple classifier as the predictor. But for example, to query bike designs using text and image prompts, we've set up a rendering pipeline for bicycle designs, which generates images from a parametric vector. And next we leverage a contrastive language image pre-training model, better known as CLIP, which calculates text and image embeddings. And we can then use this renderer and the clip model to map parametric designs, text prompts, and reference images into a 512-dimensional vector space within which we can calculate distance metrics. And this allows us to estimate the similarity of any parametric design to any text prompt or reference image. And to showcase this, we ran an example on a bike design problem using text prompts. The original design is the red road bike above. And we have 5 objectives: proximity, manifold proximity, and sparsity, as well as 2 text prompts: a black cyberpunk-style road racing bicycle and a sturdy, compact, bright blue mountain bike with thick tires. Now, to showcase how MCD trades off different objectives in this scenario, I've put together a little objective priority map here, showing what MCD samples under different weightings of the 5 objectives. So at the top of this map, the weighting of proximity, manifold proximity, and sparsity are higher. Towards the left, we prioritize similarity to the black cyberpunk bike, and vice versa on the right. And I should note that we only sample one design per objective weighting, so diversity is not really a factor in this example. So towards the top, since we prioritize similarity and sparsity, we get designs that resemble the original design. Towards the bottom, designs are more free to deviate from the query. So on the left, in the bottom left corner, designs are more similar to what we would probably conceptualize for a cyberpunk-style road bike. In the right, the designs look a little bit more like blue mountain bikes. And in the center, we have an interesting blend of features, kind of striking a trade-off between the 2 text prompts. And although these results are obviously not perfect, we're optimistic that the kind of rapid advancements we're seeing in text and image models will continue to enable stronger inverse counterfactuals in conjunction with MCD. For the final set of results today, I'd like to briefly highlight the multimodality and modularity that MCD supports. So here I showcase a similar counterfactual problem, and in this case, the second text prompt is replaced with an image, and we incorporate structural performance with the goal of maximizing safety factor, prioritized towards the top, and minimizing frame mass towards the bottom. And these 4 counterfactual objectives, I'd just like to note, span 3 different data modalities and are estimated using 4 standalone machine learning models. So MCD can be used in a very modular fashion with different modalities. And it's a little hard to see how the objectives are satisfied based on the images, so I've included some of these heat maps that show the objective scores, and it's just a little bit easier to appreciate. So this one shows text similarity, which is maximized on the left. Lighter is better. This one here is the image matching, prioritized on the right, safety factor, prioritized at the top, and frame mass, prioritized at the bottom. Now again, these results aren't perfect. You can definitely pick out some kind of infeasibilities in the generated counterfactuals, and maybe a greater weighting on manifold proximity could remedy this. But regardless, we feel this is a meaningful demonstration of the sorts of multimodal problems that MCD can help solve. All right, going to wrap up now. So I'm going to briefly summarize the key takeaways from the video. We talked about how inverse counterfactuals can serve as a design recommendation tool that recommends modifications to your particular design to meet your specific design goals. We then talked about the various qualities of strong counterfactuals and how counterfactual search can be boiled down to a multi-objective optimization problem. We then presented a bike frame design example where MCD successfully identified design alternatives that satisfy 2 competing objectives of frame mass and safety factor. And finally, we discussed how MCD can be augmented using advanced AI models to handle text-based, image-based, and multimodal counterfactuals. I want to highlight that this is a tool we're very excited to share. We've put together a package on PyPI, we've got a GitHub, we've got unit tests, the whole shebang. And feel free to check out the project page on the lab website. And last but not least, feel free to get in touch if you have ideas for new features, comments, ideas for collaboration, you name it. All right, thanks so much for watching and hope you have a wonderful day.